before we move on to some different op-amp circuits, let's take a closer look at our ideal op-amp model, and we're going to note a few things that are going to be helpful when we're analyzing op-amp circuits. So far all I've done here is just copy the same ideal op-amp model we had from the previous video. We see we have on the left our two inputs V1 and V2. Between the two we've defined this differential input voltage VD, and then our output is connected directly to this dependent voltage source, which has a value of A0 VD, where A0 was our voltage gain of the amplifier. So we're going to talk about a few key points of this ideal op-amp. The first is that this open loop gain is assumed to be infinite. And so our open loop gain is the A0. So open loop gain is assumed to be infinite. And so of course what we're saying with that is that our A0 equals infinity. So an ideal operational amplifier just has this infinite amplification power. So practically what that means for our differential amplifier is that this differential input voltage VD has to be 0. Otherwise our output is just going to go without bound. So our point 2 then is this differential input voltage VD is assumed to be 0. So we can write from our previous video, we said VD is equal to V2 minus V1. So we know that that is equal to 0, which means that V2 equals V1. So let's go ahead and box that guy in, because that's going to be an important equation that we use in our analysis. So another important thing, recall in our previous video we also drew our non-ideal op-amp model, and in that we had this resistor R sub I connected between our two input terminals. Well, with our ideal model we just leave that as an open circuit. So another way to say that, we can say in point 3, is just that our input resistance is assumed to be infinite, or an open circuit. So input resistance, I don't have it labeled here, but in our non-ideal we had that labeled as R sub I, and typically that's what we use for input resistance R sub I, and that's going to be assumed to be infinite. So we're assuming that's infinity, and we can also just write that, of course, as Ri equals infinity. And so what that implies then is if we have an infinite input resistance, we have no path for our current in the circuit up here. So if we define some current I1 here and some current I2 at our second input terminal, we know that those currents are going to be 0 because we have this open circuit. If there's no closed circuit, there's nowhere for our current to flow. So our main takeaway from here is that I1, how I've defined above, is equal to 0, and our I2, as I've defined above, is equal to 0. So these are also very important, so we're going to box those as well. Okay, so then finally, the fourth point we want to note about our ideal amplifier is that our output resistance is going to be assumed to be 0. So output resistance assumed to be 0, and so we could just write that as R0 equals 0. And we'll get a little bit into this, a little more into this later, but basically what this entails is that our output voltage Vout, in our ideal case, is going to be independent of the load connected to the amplifier. So independent of load connected to our op-amp. And we're going to see a little bit later on in this class, and definitely in some classes beyond this one, that that's not always the case, because if we have our R0 not equal to 0, what's going to happen is we're going to have a voltage divider. And so I'll come back up here and explain that a little clearer, but if we look at this circuit, so recall that in the previous video we said for our non-ideal case we of course had this Ri here, and I also had a resistor R out here. And so if we have that R out, we have this voltage source. So if we're looking at our output circuit, so we have this voltage source, we have R out, and we have some load connected to that. So all of that reference to ground. So this would be like some load, which has our voltage V out across it, and this would be our R out. And so of course, you might remember if we called this our, well, let's just stick with our notation we have, A naught VD. So we could say our V naught from voltage divider is just going to be that input voltage, which in this case is A naught VD, times RL divided by the sum of the resistors in series. And so what we can see from that equation there is that if our R naught goes to 0, then that value is just going to be A naught VD like we expect. But as that R naught becomes large relative to RL, our V naught is not going to be what we expect. It's going to be decreasing a little bit. But of course, again, here we are considering an ideal case, so we don't have to worry about our input and output resistances. So the main things that we're going to keep in mind for our analysis is that V2 is equal to V1, so our two input terminals are equal, and the current going into those input terminals is equal to 0. So essentially these three things boxed in red here. So I want you guys to get a feel for how this sort of ideal op amp compares to real op amps. And again, these ranges are just sort of typical ranges pulled from your book. There are a lot of different types of op amps, so some of them might perform better in some areas, but not as good in others. But these are just typical parameters for sort of standard op amps. So a couple of big parameters of interest. We have, of course, our open loop gain. And so I'm going to write it out just so we get used to seeing what that is. So our open loop gain is A naught. Our input resistance, Ri, is another important one. Our output resistance, and then we'll also just mention our typical ranges for supply voltage. Again, keeping in mind that this is going to vary as we are talking about different op amp integrated circuits. So let's look at, well actually let's switch this around compared to how it is in the notes. Let's first put our column of our ideal values here, what we just talked about, and then we'll compare that to our typical values. Okay, so our open loop gain, we said in the ideal case, this is going to be infinite. Well, typical cases of gain are anywhere from 10 to the power of fifth to 10 to the power of 8. And again, for specialty amps, it could be even higher than that. So we see that's a really large number, so in most cases, this approximation of infinite is going to be reasonable. For our input resistance, we said in the ideal case, that's an infinite number of ohms, so essentially an open circuit. For our typical range, we see it is again 10 to the fifth, and now we're going up to 10 to the 13th ohms. So again, pretty reasonable assumption. Our output resistance, ideally, we said was going to be 0. And in practice, we'll see it's typically going to be a matter of tens of ohms, so anywhere between 10 and 100 ohms. And then finally, for our ideal case, we don't necessarily have an ideal supply voltage, but oftentimes you'll see supply voltage ranging anywhere from 5 to 24 volts. And again, sort of the main idea behind this is with this ideal case, we're just creating a model that's a little easier to work with. And as we're going to see in some of the examples, we can do problems a lot easier and get reasonable answers without having to do all this extra work that would be required if we used more approximate values or more exact values. So in the following videos, we'll finally get into what some of these circuits look like. But before we do that, if anybody has any questions, please feel free to let me know.